Start with a fair question. Over some stretch of a curve, how fast is it climbing? Pick 2 points and draw the straight line between them. Its steepness is the rise divided by the run, the average rate of change across that interval. That line through 2 points has a name, the secant. Now slide the second point in toward the first. The interval shrinks and the secant tips and settles. In the limit, when the 2 points become 1, the secant becomes the tangent, the line that just grazes the curve. Its slope is the rate of change at a single point, and that number is the derivative.
So the impossible slope at one point is really just a limit of ordinary slopes.
Exactly. Here is the move that opens everything up. We can read off that tangent slope at every point, not just one. Do that all the way along, and the slopes trace out a brand new function. We call it the derivative of the original written f'. The top curve is the height, the bottom curve is its slope. And now the two curves talk to each other. Where the hill is climbing, the slope is positive, so f' rides above the axis. Where the hill is falling, the slope is negative and f' drops below. And right at the summit, where the curve is level for an instant, the slope is 0 and f' crosses through. The peak of the height lines up exactly with the 0 of the slope. Read one shape, and you can draw the other. There is one more way to see the derivative, and it is the one that pays off later. Take the curve and zoom in on a point, closer and closer, just as we did with limits. The bend flattens. Up close, the curve and its tangent line are the same thing. So near that point, the function does something wonderfully simple. Nudge the input by a tiny amount. The output changes by that same tiny amount, scaled by the slope. A small step across becomes a step up, stretched by the derivative. Change in times the slope gives change out. That is worth a name. The derivative is the local stretch factor, how much the function magnifies a tiny change as it passes through that point. Think of it as an instantaneous gear ratio. Hold on to that picture, because the next episode on the chain rule runs entirely on it. The cleanest example is motion. Let the curve be position over time, how far along you are at each moment. Then the slope of that curve is your velocity, your speed right now. Where the curve is steep, you are moving fast. Where it levels off, you are slowing down. The tangent slope is the needle on the speedometer. One habit before we go. We say this out loud as the derivative of position with respect to time. With respect to time just means, per unit of time, the thing we are dividing by. Say it that way, in words, and the derivative stops being a symbol and starts being a rate you can feel. So the derivative is 3 pictures of one idea. The slope of the tangent line, the instantaneous rate of change, and the local stretch factor. All of them are that same limit, the secant collapsing to a point. Next, we run the whole thing in reverse. Instead of measuring a rate, we add up a rate over time to recover the total, and that is the integral. The derivative takes things apart. The integral puts them back together.